Hello, I'm Ryan with High Desert Math Tutor, and today I want to talk to you about the differences between definite integrals and indefinite integrals. So I will begin by assuming that you're already familiar with antiderivatives, finding antiderivatives. I will still show all of the steps, step by step through integration, but as I mentioned, I want to skip over some of the details of what an antiderivative is and what leads up to this point of calculus. So to begin, we know there are two major sides of calculus. There's differential calculus and integral calculus. When we get into integral calculus, there are really two different types of integrals we could be dealing with. One type is a definite integral. The other type is an indefinite integral. Now, definite means it's clear. We know exactly what it is. Like we have a number or an answer that is concrete. We all can understand. Indefinite means that some details are missing. Maybe we have a formula as an answer, or just something that's not as obvious. And when I say obvious, I mean obvious what number it becomes in the end. So to begin, I want to show you how to find a definite integral. So in finding a definite integral, the first step is to find the antiderivative of the function. And then after we find that antiderivative, we want to make use of these limits of integration. So here's our integral sign. These numbers on the top and the bottom of the integral, those are called limits of integration. So to begin, we want to find our antiderivative. So the antiderivative of 6x squared, we first take the 6x squared. We're going to then add 1 to the exponent, and then divide by the new exponent, which is 2 plus 1. Then we take our minus 2x. Our exponent is currently 1, so we're going to add 1 to the exponent, then divide by the new exponent. And finally, we'll take our plus 1. The antiderivative of 1 is just x. And I'll go ahead and show, just for the sake of it, for completeness, that technically 1 is the same as x to the power 0. So we can still take that, add 1 to the exponent, and divide by the new exponent. But that's just a little bit thorough detail. So it looks crazy, but this is our antiderivative. Now we want to bring over the limits of integration, put them on the top and bottom of the right bracket. We have our 5, we have our 0, and now we just simplify. So we are almost done with the calculus, actually. So we have 6x to the power 3 divided by 3 minus 2x squared divided by 2 plus x. We still have the limits of integration, 0 and 5. Now, one last bit of simplifying. We have 6 divided by 3 is 2, x cubed. 2 divided by 2 is just x squared. And then we just have our x. Now we can take this simplified antiderivative and make use of these limits of integration. So you always plug the top number in first. So we'll take this function. We will first substitute 5 into this function for x. So we'll have sort of this template. The function, but we're going to plug 5 in anywhere we see an x, minus the function again, but we're going to plug in 0 anywhere we see x. So we have 2 times something cubed minus something squared plus something. Oops. 2 times something cubed minus something squared plus something. So the first number we plug in is 5 everywhere we see x. The next number we plug in is 0 everywhere we see x. Now, one detail that's very important is If you have more than one term here, it's extremely important that you put parentheses or brackets around the whole function before you subtract, just to make sure that you get the appropriate signs for all of your numbers. Now here, 5 times 5 is 25, 125 times 2 is 250. 5 times 5 is 25, plus 5. I'll go ahead and keep this in parentheses for now. Now this one is nice because we have 0 to the power 3 is 0. 0 times 2 is 0. 0 squared is 0. And when you add 0, you get 0. So the nice thing is that this whole piece goes away. And that often happens. And we really like to keep an eye out for when our work is essentially cut in half, since we still have to simplify this, but that doesn't need more simplifying, it just turns into 0. Okay, so finally, what we do is take 225, or 250 minus 25 is 225, plus 5 is 230. Okay, so this is a little bit of a long process. It's not too bad, but it gets worse if you have fractions. But in a definite integral is one where you have limits of integration, and then the process is to find first the antiderivative, do a little simplifying, then after you've simplified that antiderivative, you're going to plug in the limits of integration, where the top number is plugged in first, minus the bottom number is plugged in second, anywhere you have a variable. Then we just simplify, and we get a single number as an answer. So for definite integrals, we typically have an answer that's a number. But now let's transition over to indefinite integrals. So indefinite, not definite, means that there's going to be less detail. And, we should really step back for just a moment. What are kind of the two interpretations of integrals? I mean, integrals have, numerous uses, numerous interpretations in terms of force or area or money. But what I mean is, what are the two really concrete, just basic ideas behind integrals? Well, for one, an integral gives you the area under a curve. So let me show you. It's the area between a curve and the x-axis. So I'm going to draw an arbitrary or just kind of a randomly chosen function to represent this. This is going to be a random function, a random drawing, I mean. So I know this is a parabola. I know it opens upward, but I'm just going to draw just a quick, fast parabola. So let's just say we had this, a parabola that goes down like this and like this. So what this integral gives us is the area between this curve and the x-axis. So not only that, but we are interested in only the space between x equals 0 right here. So let's say right here. X equals 0 and x equals 5. So let's say that's right here. So we want to know what the space is, or the area between this curve and the x-axis between x is 0 and x is 5. So this would be the space between the curve and the x-axis initially. But then we transition to where we're above the x-axis, and this is the area between the curve and the x-axis on the right side of this x-intercept. So definite integrals give you the area between the curve and the x-axis. And these two numbers are typically x values, but those are the x values that tell you where to start looking for the area and where to stop looking for the area. So integrals can give you the area between the curve and the x-axis, but what's the other interpretation of integrals? Well, an integral is the opposite of a derivative. So when you get into indefinite integrals, we are not so concerned always with finding an exact number or exact area, but sometimes we just want to plain old undo a derivative, and that's where this comes in handy. So when you do not have numbers by the integral sign or numbers, limits of integration, so these numbers here are called limits of integration, as we saw here. If you don't have limits of integration, then this is called an indefinite integral, and literally we just want to find the antiderivative and then we're done. So as we saw over here, I'll walk through the process one more time, but I'll go quickly. We're going to just find the antiderivative, and I'll do it the same exact way as before. So take our 6x squared, and we need to add 1 to the exponent, then divide by the new exponent. Then we say minus 2x, add 1 to the exponent, which our exponent was originally 1, but we're going to add 1 to that, and divide by the new exponent, 1 plus 1. And finally, the antiderivative of 1 is just x. Now here, I'm sorry, I don't need the brackets at this point because we don't have these limits of integration. We need these brackets here because we have limits of integration, and having these brackets tells us which pieces of this function we should be plugging those numbers into. So here, since we don't have limits of integration, we don't actually need the brackets or parentheses, but now's the time to remember, what do we always need when we just plain old find an antiderivative? We're not doing anything else, we just want to find the antiderivative, then we're done. Well, anytime you find an antiderivative and then you just stop there, you have to add plus c. So now we can go on to just simplifying. So we have 6x cubed over 3 minus 2x squared over 2 plus x plus c. Then we have a little simplifying to do. I'll just write it out. So 6 divided by 3 is 2, x cubed. 2 divided by 2 is 1, x squared. We have plus x plus c. So that's our final answer. You see, there's less detail in what our actual answer is because this answer is a formula. When you have indefinite integrals, most often the answer you get is a formula. But when you have definite integrals, most often when you're dealing with these, because you have limits of integration and you're plugging those limits of integration into your antiderivative, two special things happen. One is we do not have plus c anymore. Not only that, but we have an actual number as an answer for definite integrals. So definite integrals giving us the area between the curve and the x-axis. We first start looking for that area at x equals 0 for this problem. We stop looking for the area at x equals 5 for this problem. But indefinite integrals are literally just antiderivatives. It's just saying, I want you to undo taking a derivative. So that's the gist of, integral calculus. But I want to give you one last bonus comment that this will be useful if your teachers are challenging. And when I say challenging, I mean they want to be extra thorough. They want you to learn more. That's usually a good thing. It's painful, but it's good. I want to give you an extra tip for that, but especially for those of you that plan to go on to Calc 3, or sometimes you'll see this in, say, differential equations, you'll see this in linear algebra. I want to talk about finding an integral, a definite integral, but one where, I'm going to put this in another color first. One where your limits of integration are actually variables. So I don't know if you can recall composition of functions, where you take one function, plug it into another function. But here, it's pretty common at a higher level of math to actually integrate a function. But what you plug in as limits of integration are not numbers, but they're actually other functions. So here, because this is a bonus comment, I'm going to make this one fast. So you notice here, we jumped straight to our antiderivative. We can jump straight to the antiderivative now. We have 2x cubed minus x squared plus x. We saw the same one over here, 2x cubed minus x squared plus x. We're going to jump from here straight to this antiderivative since we've already done this work twice. But this is a definite integral because we do have limits of integration. So we do need to put the brackets, and we also need to bring over our limits of integration to the right side of either brackets or parentheses, whatever you prefer to use. So at this stage, we're just going to do what we did here originally. We're going to take the limits of integration, whatever they are, we're going to plug the top one into this function first. Then we're going to subtract what we get when we plug the bottom limit into the function. So I'll just set up the template. We have something minus something. We have 2 something squared, cubed, minus, ooh man, I'm getting all over the place now. Something squared plus something, 2 something cubed minus something squared plus something. So what we're plugging in first is x squared from right here. X squared, x squared. Next, we're plugging in just plain old x. X, x, and x. So I'll assume you're reasonably comfortable with the algebra. What we get here is 2x to the 6th minus x to the 4th plus x squared minus 2x cubed minus x squared plus x. And is there anything we can combine? Yes, there is. Okay, so we see there is minus x squared, or plus x squared minus x squared. I'm sorry, I'm looking ahead. These cancel. So our final answer is just 2x to the power 6 minus x to the power 4 minus 2x to the power 3 plus x. Notice here we have a formula as an answer, but we do not need plus c. This integral had limits of integration, which means it's a definite integral. And definite integrals give you the area between this curve and the x-axis. And even if these limits of integration are functions, it's kind of weird, it's hard to process, but we have something that gives us an area. And here we don't need plus some constant number because plus c only applies to indefinite integrals. When you're just finding an antiderivative, then you're done. So one last note and then we'll call it a day. So definite integrals, I hope you can see this, do not have plus c. And indefinite integrals must have plus c. All right, so I hope that's enough to get you started with really clearly seeing the difference between definite integrals and indefinite integrals. I hope this clarifies when you should have plus c. You do not have a plus c with definite, but you do have plus c with indefinite. And finally, just for those of you that are either moving on to Calc 3 or you're hoping to really just understand this at a much higher level, it's very common, especially when you're in physics, to deal with integration, but what you plug in for limits are actually formulas and variables instead of just simple constant numbers.